Did you know you can measure RPM using just a mobile phone or a tablet? The app I'm using for this is called Spectrum Analyze, and it's a free app, though I paid $1 to unlock some very useful features. Let's measure the RPM of my jointer. So the fundamental frequency of this jointer appears to be 240 Hertz, and that repeats every 240 Hertz. If we look here, that is at 480, so twice that. So basically there's a lot of resonances to that main frequency, and that's the rate at which the knives go past the table. So let's go to the calculator, and we have 240 Hertz, and I know there's 3 knives on the head, so it turns 80 times per second times 60, 4800 RPM on the cutter head. Next, the table saw. So we have a very strong fundamental peak at about 3020 Hertz. So 3020 divided by 40 teeth on the blade is 75.5 turns per second, times 60 seconds in a minute is 4530 RPM. Now it's not quite that straightforward. You kind of have to know what you're doing and know what approximate RPM you're looking for, because if I zoom way out on this, you can see all kinds of peaks here. These are multiples of the tooth frequency because they don't just excite the frequency of the teeth, but also essentially harmonics of it. And if we zoom in way on the left at the lowest frequencies, we see some weaker peaks there. For instance, this one here, that's at 120 Hertz, and that's essentially just line hum from the motor. This sort of line hum is quite common. There's also 120 Hertz coming from the transformer in this battery charger. Transformer hum is always double the frequency, so the transformer gets 60 Hertz and the magnetic field will vary 60 times per second, but as the magnetic field maximizes in one direction, the force is maximum. Then as it crosses 0, the force is nothing, but then as it goes in the other direction, the force is again the same amount. So for every cycle that goes both up and down, the magnetic field peaks out twice, so you get twice as many peaks in the magnetic field, causing a hum of twice the frequency. Next, let's measure this dust collector. So we have some interesting peaks. We have one at 354 Hertz, and there's one back here at very low frequencies. This one is at 59 Hertz. So it works out that 354 is 59 times 6. And that tells us this is probably the motor frequency, the rate at which the motor is turning around, and this is for the vanes, so that the impeller on this blower has 6 vanes, causing 6 times the frequency. So we take the 59 turns per second times 60 is 3540 RPM. But if we look at the tag on the motor, it says 3450 RPM, and I know the no-load speed of these motors is 3600 RPM. It's rated for 3450 and it's actually running at 3540. So the rated speed is 95.8% idle speed, and the actual speed is 98.3% idle speed. So it's rated to run 4.16% below idle speed, but is actually running at 1.66% below idle speed. So basically the speed drop from idle is only 40% of what it's rated for, which is to say this motor currently is only 40% loaded. So we have a very pronounced peak at around 1872 Hertz. It's divided by 6 teeth per inch on my blade, comes to 312 inches per second. Divided by 12 inches in a foot is 26 feet per second, times 60 seconds in a minute is 1560 feet per minute. What's the speed of my Dremel tool? So looking at the spectrum here, we have 2 strong peaks that are close to each other. I'm not sure which one of those actually represents the RPM. One is at about 547, the other one is at 671. So I'll put a small piece of tape on the chuck to get more sound from that, and we'll try again. So before we had those 2 peaks, now we just added this peak. I'm guessing that this tape slowed down the Dremel a little bit, so I'll shorten it a bit to put less load on it, and let's try again. So with less load, we get about this frequency. Oops. And that works out to 506 turns per second times 60 is 30,000 RPM. Now, curiously enough, we have another peak in here as well, and it turns out those two peaks are 120 Hertz apart. So that is some intermodulation between the actual rotation of this thing and the line hum. So let's take the tape off and try this again. And I think those two peaks that we saw earlier are just 120 Hertz apart. So we have one peak at 539, and this other peak is at 659. That's exactly 120 Hertz apart. So going back now, I know that this was the actual idle RPM at 543 turns per second is 32,580 RPM. What's the speed of this fan? A very clear peak here, which is at 70 Hertz. 70 Hertz divided by 3 blades on the fan is 23.3 turns per second times 60 seconds is 1400 RPM. Question is, does the filter in this fan slow it down? Here's our 70 Hertz again. Let's take the filter out. And sure enough, it speeds up. What's the speed of my router on the Panther router? So if we look on here, the first real strong peak is 268 Hertz. Times 60 seconds in a minute is 16,080 RPM, which happens to be very close to what this router is actually set to. Now looking at this some more, there's some other peaks on here as well. For instance, we have this peak here, which is 120 Hertz. That's the line frequency. We also have this peak, which is 120 Hertz higher than the speed of the router. So that's 120 Hertz intermod. I don't know what this one is for, but if we zoom way out, way out, we can see a very strong peak here. That one is at about 4800 Hertz. That happens to be 18 times the actual frequency that we're getting off the router. So that tells me that is probably the commutator noise and that the motor has 18 points on the commutator. So as you can see, it's not always entirely straightforward. It helps if you have experience using spectrum analyzers. The app I'm using on here is called Spectrum Analyze for Android. It's a free app. The upgrade for $1 allows me to zoom in better. Well worth it. The other thing you want to do is you want to set it so it's got 32,000 bins on the FFT. I tried to find an equivalent app for iOS, for iPad, but most of the apps on iPad tend to cost a fair bit of money. I bought a few of them, but none of them turned out to be as useful as this one. There are a few that cost on the order of $20 to $30 that I didn't try, because if you spend that much money, you could just spend that money buying a cheap RPM meter from China.